Hey, what's up everyone? Welcome to Descriptive / Lab Chemistry Part 1. Today we're going to be discussing types of reactions. So in chemistry, there's going to be a lot of reactions, nearly an infinite amount of reactions, but many of them can be categorized into one of 5 types, and we're going to go over all these 5 in depth. So first of all, we have synthesis or combination reactions, and they have the general form of A plus B producing AB. So A and B could be elements like carbon and oxygen combining to form CO2, or they could be compounds like H2O and SO3 producing H2SO4, or water and carbon dioxide creating H2CO3. And these 2 reactions are the cause of acid rain, and they're also the reason for why rain is normally acidic. So H2O is water, so when it rains you have water coming down from the atmosphere, and then you have SO3, which is a major pollutant, and they combine to create H2SO4. So when the SO3 reacts with the water, you create sulfuric acid, and that's the reason of acid rain. But you can also have carbon dioxide in the atmosphere on its own, and sometimes that reacts with the water to produce H2CO3, which makes rain on its own normally acidic. Now, if you notice, there's something interesting about the oxygen here, and the fact that the oxygen has a 2 on it. Now, if we're talking about a synthesis or a combination reaction, shouldn't the oxygen be on its own? What is it doing with the 2? Well, the thing is, oxygen is something known as a diatomic element. So diatomic elements are elements that occur naturally as pairs. And you have a couple of them. You have hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. And if you have trouble remembering it, just think of the mnemonic, have no fear of ice cold beer. That's a really common one people use to remember this. And so all these elements are going to be in their diatomic form. If you're ever balancing an equation and you have one of these just on its own, make sure to put a 2 as a subscript. Now, hydrogen, nitrogen, fluorine, oxygen, and chlorine are gases at room temperature. Bromine is a liquid at room temperature, and iodine can be a liquid or a solid, depending on certain conditions. But this is by far the most important bit of that. The fact that the hydrogen, nitrogen, fluorine, oxygen, chlorine are gases at room temperature. That information will become a bit more useful when we start talking about gas evolution reactions, but just have that in the back of your mind for now. Now, there's one more thing about synthesis or combination reactions that I want to talk about, and it's the fact that when you go to combine them, you shouldn't combine them in just H2O2. You don't just take AB and make AB. And the reason for this is because you have to look at oxidation numbers. An oxidation number is the charge an atom would have if it had purely ionic properties. So you have a table of ionic charge here, and the thing about these is that when you create compounds, all your compounds must have a charge of 0 unless otherwise stated. So if you look at H2O2 here, H2O2, hydrogen has a charge of +1, so you have 2 hydrogens with a charge of +1, and you have oxygen. So oxygen has a charge of -2, so you have 2 times -2, and what that gives you is that you have an overall charge of -2. You can't have that. So you have to determine what combination of hydrogen and oxygen do you need in order to have a charge of 0. So you know you're going to have some hydrogen and some oxygen, and you know hydrogen has a charge of +1 and oxygen has a charge of -2, and a combination that works is H2O. So you have 2 hydrogens, which is +1, and you have 1 oxygen, which is -2, and that results in an overall charge of 0. So really, the synthesis reaction that's happening here is that H2 and O2 are reacting to form H2O. Now, the last thing that you have to do with this reaction is balance it, because if you notice, the atoms are not balanced. But that's really simple. You just balance it, and you get that 2 hydrogens are reacting with oxygen to produce water. Now, although this is a process I introduced in synthesis or combination reactions, you need to make sure all your other types of reactions follow this as well. So let's talk about the next type, which is a decomposition reaction. Decomposition reactions have the form of A and B decomposing into A and B. So in a decomposition reaction, you can have compounds that break up into elements like you have here. So water is breaking up into hydrogen molecules and oxygen molecules, or you can have a compound breaking up into other compounds like we have here. So CaOH2 is breaking up into calcium oxide and water. pretty straightforward. And as always, you have to make sure all the charges balance out. So if we look at here, the water has a charge of 0. If you look at here, although it kind of doesn't make sense for these to have charges of 0, the fact that they're diatomic and they're just on their own as atoms means that they have a charge of 0. And the same for the oxygen. The compound here, calcium, CaOH2, calcium has a charge of +2, and OH has a charge of -1, but you have 2 of them, so it's -2, so that comes out to 0. If you look at calcium oxide, calcium has a charge of +2, oxygen has a charge of -2, so that's 0. And water, hydrogen has a charge of +1, you have 2 of them, so +2, and oxygen has a charge of -2, so all that comes out to 0. So as you can see, all the ionic charges here cancel out. So let's look at the next type, which is a combustion reaction. In a combustion reaction, you have something, A, and A is usually a hydrocarbon, and it's reacting with oxygen to produce carbon dioxide and water. For example, if you have methane reacting with oxygen to produce carbon dioxide and water. This is the reaction that happens in stoves. So you have CH4, which is natural gas, and it reacts with the oxygen to produce carbon dioxide and water. And also, as a byproduct, you have a lot of heat that's also being generated here. So that's what's used to power stoves. And you also have something like CH3OH reacting with oxygen to produce carbon dioxide and water. And again, these are hydrocarbons. So a hydrocarbon is a molecule that's purely just carbon and hydrogen in with some subscripts. Now, they're usually hydrocarbons because you can have other things attached to these hydrocarbons, like for example, you see an oxygen in the one here. But a lot of the times they are going to be hydrocarbons or very, very similar to a pure hydrocarbon. The next type is a single displacement reaction. So these reactions have the general form of A plus BC producing B plus AC. So as you can see, the A takes on the C and the B goes on its own. So in these types of reactions, you kind of have two different scenarios. The first scenario is you have a cation replacement. So if you have zinc is going to pair up with the chloride here, and copper just goes on its own. Since the zinc is pairing up with the chloride, which generally has a charge of -1, this tells us that the zinc is a cation and it's getting replaced in this single displacement reaction. On the other hand, you can have something like an anion, like bromine. And bromine pairs up with the potassium here because it is an anion. And potassium has a +1 charge, so the bromine pairs up with the potassium, and iodine is left on its own. If you notice, the redox numbers for all of these match up. All the charges of these compounds are going to be 0. And so zinc is on its own, so it's 0. Copper has a oxidation number of +2. Chloride has an oxidation number of -1, but you have 2 of them, so it's -2. And you can do the rest for all of these, and they'll all come out to 0. And that's the beauty of these types of reactions. We'll look more into the oxidation numbers of the individual atoms within the compounds later when we talk about redox reactions. But for now, a single displacement reaction has the general form A plus BC producing B plus AC. And so you can have a cation being paired up with an anion, or you can have an anion being paired up with a cation. And single displacement reactions are very frequent when we're talking about redox reactions. Now, the last type of reaction that we're going to go over is a double displacement reaction. And so in a double displacement reaction, you have AB reacting with CD to produce AD and BC. So the inner ones come together and the outer ones also come together. So inner with inner, outer with outer, then you have a double displacement reaction. So in double displacement reactions, A and C are cations and B and D are anions. And if you realize, the reason the inners go with the inners is because both the inners are opposite. So the inner is inner B and C. B is an anion and C is a cation. The outers, A and D, A is a cation, D is an anion. So you need a cation and an anion paired together. And again, this is all to balance out those oxidation numbers, those ionic charges. Okay, let's do a practice problem. So let's try to balance out the barium chloride with silver nitrate and see what the products are going to be. So we have barium and chloride. So barium is the A, chloride is the B, silver is C, NO3 is D. So we know A and D are going to go together. So we know barium is going to be paired up with NO3. But we need to figure out what the subscripts are, because barium has a charge of +2. Barium has a charge of +2, and nitrate has a charge of -1. So that means in order to balance out the charge of this, we need to have 2 nitrates. And so you would need a 2 on the nitrate here. And so let's worry now about Cb. So C is the silver, so silver, and then you have chloride. Silver has a charge of +1. And the reason we know this is because we know for a fact that nitrate always has a charge of -1. So in order for this compound to have a charge of 0, silver must have a charge of +1. And the thing about a lot of transition metals is that they can have different charges based on the compounds that they form. But in this case, our silver has a charge of +1, and chloride also has a charge of -1. So that means our expression here is balanced on its own. The charge of this compound is 0. The last thing we have to worry about is making sure that the atoms are balanced, so making sure to balance the chemical equation here. We have 2 nitrates on the right hand side, but only 1 on the left hand side, so let's add a 2 here. But now we have 2 silvers on the left hand side and only 1 on the right hand side, so let's add a 2 here. And after that, everything balances out. So our final reaction is barium chloride reacting with 2 silver nitrate to produce barium nitrate and 2 silver chloride. And that is our final balanced reaction. Let's do one more. Let's try balancing out calcium carbonate with hydrochloric acid. So we know A and D are going together, so it's going to be calcium with chloride, and C and B, so we have H and CO3. The calcium has a charge of +2, the carbonate has a charge of -2, hydrogen has a charge of +1, and chloride has a charge of -1. So that means since we have calcium pairing up with chloride, we need a 2 on the chloride here. And since hydrogen is pairing up with the carbonate, we need to add a 2 here. Last thing to do is balance out the chemical reaction. We have 2 hydrogens on the right hand side, so let's add a 2 here. And after that, everything else looks balanced. So that is our final balanced chemical reaction. If you react calcium carbonate with hydrochloric acid, you're going to produce calcium chloride and H2CO3, carbonic acid. Double displacement reactions are really common, and they are really important because a lot of reactions use a double displacement reaction. And some examples of these are acid-base neutralization reactions, precipitation reactions, and gas evolution reactions. We'll go over all these reactions in further detail later, but for now that's it. That's the 5 types of chemical reactions. If you know those 5 types, then you can predict the products of almost any reaction that you come across. That's all I have. I hope to see you later, and thank you for watching.